regularity property of measure, Leibniz measure. The theorem statement is correct. The following statements are equivalent. So first one, number 1, a set E is measurable. Okay, throughout this Leibniz measure discussion, E is a subset of R. Second one, for every epsilon, epsilon greater than 0, there exists an open set U containing E such that so measure of E, U minus E is less than epsilon. The third one, there exists intersection of open sets, that is G delta set. There exists as G delta set. Take this as G containing E such that measure of G minus E is 0. Okay. Here the statement about the set E and the U, but okay, U is open set, so no problem about the measurability of U. Okay, if we assume E is measurable, then M of E exists, U minus E is measurable. But only if we consider it 2 alone, we don't know whether U minus E is measurable or not. First of all, we don't know whether E is measurable or not. So okay, only say that outer measure of this is 0. And the fourth property, for every epsilon greater than 0, there exists a closed set G containing E such that M star of E minus G. Now closed set I am going to denote it by capital C or F. E minus F is less than epsilon. Fifth one, in intersection of union of closed sets, there exists a F sigma set and F sigma set. I denote it by F contained in F such that M star of E minus F is 0. Okay. So we prove the results one by one. If we assume E is measurable, then we write M of U minus E something. No need to write M star. Okay. Once E is measurable, you write M. If you don't know about the measurability of E, we calculate outer measure. It's a proof of regularity theorem. First assumption, the following way we are going. Right? 1 implies 2, 2 implies 3, and 3 implies 1. Right? The another part, 1 implies 4, and 4 implies 5, implies 1. First we assume 1. Assume that's proof direction. 1 implies 2. Assume that E is measurable. Then we have a result that there is an open set. Right? We consider two cases. If E is finite, then what happened, and E is infinite, then what? Okay. So case 1, letter 1, measure of E is finite. Then let us take epsilon. Let epsilon greater than 0 be given. Then there exists an open set U containing E such that M of U is less than or equal to M of E plus epsilon. Right? Based on the assumption that E is measurable, we write M of U notation. We skip the notation star in front of the notation. Okay, now, what about this U minus E? We are able to calculate the measure of U minus E because E is a finite measure. So this is M of U minus M of E. This is less than epsilon. Okay. So in the case of E is of finite measure, therefore M of U minus E is finite, less than infinity. Case 2, suppose M of E is infinity, then it can be written as a countable union of set of measure, set of finite measure. Okay, since R can be written as union of the intervals where each IN is finite. This is finite interval. That means its length is finite for all n. Now let us set En equal to E intersection En. Then union of En is exactly E, and measure of En is finite. So for each En, M of E is finite. By case 1, there exists an open set Un containing En such that less than epsilon. Right? So the case 1 is true for any epsilon, right? For any epsilon. Okay? For in case 1, if measure of E is finite, then M of U minus E is finite, less than infinity for any epsilon. In the case la enna panna endha epsilon ku true irukadnala na inga enna eduthukren epsilon by 2 power n eduthukren. Endha epsilon ku true, epsilon by 2 power n ku true. Okay. Then what about the sum of all Un minus En is less than sum of epsilon by 2 power n, that is less than epsilon. Okay, so we are going to construct open set containing E such that measure of U minus E is less than epsilon. E is union of En. So obviously we have the union of, if you want the E should be contained in an open set, then you have to take the union of all open sets. Eங்கிறது union Enோட union இல்லையா, ரைட்? En எல்லாமே Un ல இருக்கு. E contain பண்ற மாதிரி ஒரு open set கொண்டு வரணும்னா union of En தான். So let us define U equal to union n from 1 to infinity. So it's a countable union of open sets, union of open sets. So clearly U is open and E contained in union of En contained in Un contained in U. So this is contained in U. So we only calculate measure of U minus E. So what about this measure of U minus E? This is measure of union n from 1 to infinity Un minus E. Okay. Which is less than or equal to summation n from 1 to infinity measure of Un minus E. Right? Since E contained in En, actually En contained in, by the construction of En contained in E. So U minus En contains U minus E. So this is less than or equal to cycle. The other is correct. And also E, Un minus En contained in this. Summation n from 1 to infinity measure of Un minus E. Because Un minus En is a superset of Un minus E. Okay, here bigger set is removed, small set, which is less than or equal to epsilon summation n from 1 to infinity epsilon by 2 power. Therefore measure of U minus E, this is epsilon less than epsilon. Somewhere you write this here epsilon. So for both cases there exists open set U containing E such that measure of U minus E is less than epsilon. Therefore 2 holes. Hence 2 holes. Now we assume 2 holes. Then prove that. So we prove that there exist G delta sets such that the difference, measure of the difference is 0. Right? If you want to prove something is 0, then you prove that it is smaller than all. Okay? It should be a non-negative number and it's smaller than all the positive numbers. Okay? So we take this some number is some number has value 0, and it must be non-negative and is smaller than all the positive numbers. In fact, you take a sequence converging to 0, you will ask, okay, prove that this number is less than 1 by n for all n. Then if it is non-negative, then this is exactly 0. So for that, for each n, we are going to apply 2 for 1 by n. For each n, there exists an open set Un containing E such that measure of Un minus E is less than 1 by n. Now we construct the G delta set as the intersection of these open sets. Okay, let take G equal to this G is a G delta set. Intersection of open sets. What about the measure of G minus E? G is a subset of Un. So this is less than or equal to measure of Un minus E. Okay, each Un minus E has measure less than 1 by n. Okay, implies m of G minus E less than or equal to 0. Already measure is non-negative. Therefore, measure of G minus E is exactly 0. Now we therefore 2 holes, 3 holes, hence 3 holes. Now the last part, that assume that statement 3 holes, and we prove that E is measurable. Here we have used small change because we have assumed that 2 holes. So 2 is written for the outer measure. So you only write this for outer measure. So I write everywhere m star of. Okay, assume by the assumption of 2 that we don't know whether E is measurable or not. So U minus E, okay, for U minus E we only calculate outer measure. So assume that 3 is measurable. Means let G be a G delta set containing E, then such that the outer measure of G minus E is 0. Since we know that if set has measure 0, then it is measurable. Since any set of 0 measure is measurable, 0 outer measure. Is measurable. So G minus E is measurable. G is a G delta set, it is measurable. G is measurable. Any G delta set is measurable. Do you know that G is measurable? G is also measurable. So now we take the diagram of G and E. G is the set containing E. Okay, the whole set is measurable. Whole set G is measurable. This set is measurable. Green line is set. Right? The difference is measurable. This set is measurable. This set is measurable. So we write E as the difference of E is obtained from G by eliminating G minus E. Right? Since by the set theoretic property, E is written as G minus E. Whatever numbers not in E is removed from G, we get. Because G is a subset of E is a subset of. So E is measurable. G measurable, G minus E measurable. So therefore E is measurable. One course. So we have proved that 1 implies 2, 2 implies 3, 3 implies 4. So now we prove that the other part, 2 implies 4, 4 implies 5, 5 implies 1, using the above part, that the equivalence of 1, 2, 3. So first assume that E is measurable. So what about the this? Okay. But we know that 2 implies 1 implies 2. Right? So what we know is if we have a epsilon greater than 0, there exists a open set U containing E such that U measure of U minus E less than epsilon. So this we know for okay E. But what we need is if you okay we must need okay a closed set containing E. So what about the complement of this closed set F? F complement open, it contains E complement. So in the place of open set U, we have F complement. So we apply the statement 2 for F complement. Okay, then we arrive at this. So let us take epsilon greater than 0 be given. Then we apply 2 for E complement. That means there exists an open set U containing E complement such that measure of U minus E complement is less than epsilon. So let us take G F equal to U complement. Then one thing is clear. F is U complement contains E. Right? And F contains E. Containing E. F is containing E. Because we have U subset of U a superset of E complement. If we take a complement, we will have other side. So F containing E. So what about the measure of E minus F? E minus F is same as F complement minus. What about these 2 sets? This is for second rough use. Third one is E minus F is nothing but F complement minus F complement. How can you prove this? If we take X in this side, X in E, but X not in F. If X is not in here, then it is in F complement. X is in E means X not in E complement. So what we have is that F belongs to F complement, but X not in E complement implies F complement minus X belongs to F complement minus E complement. Other way also true because okay we apply the complement. So this is measure of okay F complement minus E complement. Measure of what is the F complement? U minus E complement. Measure of U minus E complement is less than epsilon. Therefore, measure of E minus F less than epsilon. புரிஞ்சதோ யாருக்கெல்லாம் புரியல இது வரைக்கும் பண்ணது ஏதாவது டவுட் இருந்தா கேட்டுங்க if you have any doubt please ask me chatல வாங்க அல்லது கேளுங்க லைன்ல இருக்கவங்க வாங்க யாருக்கெல்லாம் நெட்வொர்க் நல்லா இருக்கோ அவங்களாம் வாங்க clear chat box. Sandhya, Rohini, follow பண்ண முடியுதா? சிவதர்ஷினி. Okay, so therefore, hence 4 holes. Okay, now we assume 4 and to prove, assume that 4 is true. Okay, we prove 5. Okay. Similar to already we know that 2 plus 3, we apply that. Place 3 into that type number. Yes. என்ன ப்ரூவ் பண்ணா 4 implies 5. அது காம்ப்ளிமெண்ட் வழியா தான் அப்ளை பண்ணணும் இல்லையா? Okay, we use the result 2 implies 4 for the complement. Okay. எப்படி எழுத போறோம்? 4 true அப்படின்னு எடுத்துருங்க. 4 true na given epsilon, that is given epsilon. There exists a G delta sets G containing E such that measure of G minus E is the outer measure of this. Right? This is now G delta set E complementary solver. Right? So by 4 is true. Otherwise, we directly use that. Okay. For each, so easiest way is for each n, there exists a closed set Fn contained in E such that m star of E minus Fn less than B. Okay. We construct this set as union of all closed sets. Then F is F sigma sets. In the outer measure of the containing contained in Fn E. So each Fn is contained in E, it is union of Fn contained in E. E minus F is the measure of E minus F. F is a subset of Fn. So this is a subset of Fn, we know that subset of F. So E minus Fn contained in E minus F. So outer measure of this set is bigger. So here I will take less than or equal to measure of outer measure of E minus Fn. This is true for all E. Okay, this is less than 1 by n. So m star of e minus e is 1 by n for all n implies. M star of e minus f is less than or equal to 0, not equal to 0. So 5 holds, 6 holds. 5 holds. Now assume 5 to be whole. Let me prove that 1 is to be proved. We prove that E is measurable. Now, by the assumption that there exists f sigma sets f contained in E such that m star of E minus f is 0 implies E minus f is measurable because if the set has outer measure 0 then set is measurable. So in the whole set E, right, E minus f is measurable. F can be written as, since f is E minus f, E is measurable. E is, we have to write E as a measure. F is measurable, right? Because f is f sigma set. Also, that so we have that f is measurable. Then E can be written as, since E is nothing but E minus f union f. So E minus f measurable union of two sets measurable. So E is measurable. Hence we have proved that 1 implies 4, 4 implies 5, and then 4 implies. That's all the theorem, right? Regularity theorem. So if you want to prove that a set is measurable, okay, we show that it is approximated by an open set in terms of its measure. Difference of open set and the set is difference of measure of the open set and the set different. Measure of the set is very small, arbitrarily small, then your set E is measurable. So measure of every, so the statement 2 says that for every epsilon greater than 0, if E is measurable, under the condition that E is measurable, there is an open set. Open sets U containing E such that measure of U minus E is less than epsilon, or we write measure of right. It says that every set, measurable set, is approximated by measure of. Then M of U can be written as, M of E is written as M of, this set has finite measure, right? M of U minus E has finite measure. So we write M of E equal to M of U minus M of U minus F, right? If U or a U minus F has finite measure, then we write M of E equal to M of U minus M of U minus F, right? And from this we write M of U m of E equal to m of U. Okay, it's little small. In the place of m of E minus F, E minus E. And what about the measure of E? See, it is very small, so it can be negligible. Arbitrarily small, when you take a very small epsilon, the measure of U minus E is negligible. So this measure of E is approximated by measure of, in the case of E is measurable. So this theorem tells that every, also by the fourth part, every measurable set, if E is, a set is measurable, whose measure can be approximated by measure of some open closed set contained in there. So 2 is nothing but every measurable, 2 and 1, every measurable sets, measure of any measurable set can be approximated by, or every measurable set. E, its measure can be approximated by the measure of some open set containing. The other way also true. If the outer measure of some a set is approximated by measure of some open set, okay, then the set itself is measured. And the fourth one says that the same statement for closed set, for every measurable set E, its measure can be approximated by the measure of some closed set contained in E. So its measure is approximated by the measure of some closed set F contained in E. So further we combine these two results. Okay, if we have m of E, E is a measurable set. So combined with 1, 2, 4, E is measurable. This is another kind of regularity theorem. Okay, very nice sets are closed and open sets. We don't know about the measurability of E, but it is measurable. We are not able to find the measure of E, then it can be approximated by measure of some smooth sets. So E is measurable even only if there exist an open set U and the closed set F such that F contained in E, E contained in U, and measure of U minus F is less than epsilon. Right? So the measure of the difference of U minus F is less than epsilon, obviously measure of this. And also one more statement from this statement from 1, 2 and 4. What about other second part of regularity theorem? 1, 3 and 5. E is measurable even only if there exists G delta sets, G and F sigma sets, F such that F contained in G, E contained in G, and measure of G minus E is 0.